I can start introducing Dmitry. So Dmitry Berenson is an associate professor in electrical engineering and computer science and Robotics Institute at the University of Michigan. And before coming to University of Michigan, he was an assistant professor at Worcester Polytechnic Institute, and he received his PhD degree from the Robotics Institute at Carnegie Mellon University in 2011, where he was supported by an Intel PhD fellowship. And afterwards, he was also postdoc at the UC Berkeley, and he has received the IEEE RAS Early Career Award and the National Science Foundation Career Award. And his current research focuses on robotic manipulation, robot learning, and motion planning. So thanks, Dmitry, for being here. And the floor is yours. And I just want to remind people that if you want to ask questions, you can use the question and answers in the Zoom. You can use the Slido channel and also the YouTube chat, and we will be monitoring these channels. So thanks a lot.
Hey, thank you, Martina, and thank you to the organizers of the workshop for the invitation. I'm very excited to be here, and I love that these workshops are becoming more common because it means our field of deformable object manipulation is gaining some prominence. So I'm very excited about that. But that's not how it always was. You know, when I started working in this area, people would ask me, why are you working on this niche problem? You know, it's really hard. Why not just keep working with rigid objects like everybody else? And, you know, the easy answer to that question is to say, look at all these great applications, right? We have cloth manipulation for domestic tasks. We have food preparation, manufacturing, we have surgery. Clearly, this is an important problem. But to be totally honest, that's not why I work on this. It's great to put in a grant proposal that there's some great applications, but personally, that's not my motivation. My motivation is actually to start to challenge the assumptions that have guided robotics so far. Assumptions that have enabled so much great work in robotics have now become somewhat limiting. So what assumptions am I talking about? Well, things like everything is rigid, that we know all the dynamics of everything, that we have simple uncertainty distributions, that we're working with fully actuated systems, and so on. Right? All of these have allowed us to make progress, but now we're seeing the limitations of them, and we have to start to relax these assumptions. And that's why I think that deformable object manipulation is what I call robotics complete, in the sense that people used to use the term AI complete. So if we are able to solve you know, to a sufficient degree of performance, deformable object manipulation, we will also have solved some of the hardest perception, motion planning, control, and reasoning problems that there are in robotics, and our solution should be able to propagate out from our applications to many others. So, with that context in mind, what I'm going to be talking about today is focusing on modeling deformable objects, and specifically being aware of the limitations of models. So there are many models for deformable objects out there, many types of models. So mass spring, FEM, meshless models, and probably in the last year there's been, you know, 3 or 4 more models proposed that aren't on this slide. And these models are great. There are trade-offs between expressivity and computation and things like that. But the upshot that I want to convey here is that none of these models is perfect. There's no model that captures every possible behavior of a deformable object. They're specialized to certain regimes. Nevertheless, people have used these models in, for instance, motion planning work for many years now. And in this work, it's very interesting motion planning, but the way that the models are used is basically as totally trustworthy. Whatever the model predicts, we just believe it. We have a little call to a simulator inside of our planner loop, and whatever the simulator tells us is what we use, and we just trust that completely. I think that's really unrealistic for deformable object models. We also see some very interesting work in control, using all kinds of different models, some from our work, some from David Navarro Alarcon's work, or Dinesh Minocha and Jia Pan, many different kinds of control methods for deformable objects. But again, there's this trust that we can kind of assume this model that we're using is more or less correct or has some kind of simple uncertainty distribution. Okay, so the question that I want to be asking, and we've been asking for several years in my lab, is what do we do when that's not true? What do we do when our dynamics models are unreliable? Now, please understand that unreliable doesn't mean bad. It doesn't mean useless, right? It means that there are some things the model is good at and some things it's not good at, right? And so what we want to do is use models. Of course, we need to use models, even if they're learned models. But we also need to learn to avoid a model's mistakes, okay? We're not going to be told a priori where is this model useful and where it's not. We need to be able to figure that out on our own and still perform useful tasks. So today I'm going to be talking about two very recent papers that are on this subject. One of these works, just published in Science Robotics in the May issue, is about using a learned model. So we're learning a model from data for deformable object manipulation, specifically rope here. And we want to understand when is it valid and when is it not. And the other work I'm going to talk about is using what we call a simple model, which has a different kind of application when we don't know the state space of the object that we're encountering. So let's start first with the learned model. So this is the work of my students, Peter Metrano and Dale McConaughey, who's now at TRI. And what Peter and Dale were looking at were the following questions. First, we wanted to say that we don't know the dynamics of a deformable object a priori, right? We want to learn these dynamics. But the traditional way to do that is to just gather a huge data set for a given task and try to learn the dynamics from that. And actually, that's not going to work in the kinds of tasks that we're trying to do. So instead, what we're going to do is learn the dynamics in an unconstrained environment. And now we'll have a dynamics model. And then we'll learn a classifier that tries to predict when is this dynamics model reliable in actual constrained environments where we want to use it. Now, you might say, well, that's great. You can maybe use this classifier to avoid unreliable transitions or actions when you're doing planning, but you still have a big problem in that your start state might be in a place where your model is unreliable. So we also developed a way, again, based on learning, to learn how to recover when our model is in a state, when our system is in a state where the model is not reliable, so that we can move towards a state where it is. So I'll go over this work in a little bit of detail, but I really encourage you to read this paper as there's much more detail there. So the first step to this process is learning dynamics. Then we're going to basically figure out when the dynamics are valid and how to recover when they're not. And then we're going to use these dynamics in a planning and execution architecture. So let's start with learning dynamics. So let's say we want to do tasks in this kind of tabletop scene where we want to move the rope center to a given position, right? And as you can see, we don't just have a static scene. We do have a static scene, but there are many possible object arrangements in that scene. So what we're arguing in this paper, and our results actually bear this out, is that trying to learn all the dynamics of the rope as it interacts with obstacles and catches on things and slides on things and so on is very difficult. And this would require a huge data set. I don't even know how huge it would be. We haven't found the right size for actually learning these kinds of dynamics reliably. So that's really hard. And what we're arguing is that it's much simpler to learn dynamics in this kind of unconstrained environment. And in fact, we show this in our results that we do learn good dynamics here. And then to use these dynamics in the constrained environment where they're valid. Now, again, if you are doing this, you're basically sacrificing things like catching the rope, right? We're never going to be able to model how we catch the rope on obstacles. But we're still saying, hey, this is worth it because we can still do a lot of useful tasks, even staying in regimes where the dynamics of the unconstrained dynamics are valid. Okay, so the first step to learning the dynamics is then to collect a bunch of data in this unconstrained environment. And here we're rolling out random trajectories, not purely random, there's some bias in the randomness, but anyway, they're randomly generated and we get a reasonable sized data set, nothing on the order of millions, but thousands and thousands of data points here. And then we can take that data and we can learn a dynamics function from it. This is this model where we're just adding the dynamics function to the current state. Turns out this structure is way easier to learn than if you just eliminate this ST here. So we actually don't need a very complex network. We just have two fully connected layers here, and we can learn these dynamics very well. Okay, so now we've learned some unconstrained dynamics. When are they going to be valid? Well, we could hard code a bunch of domain knowledge like, well, if it's in collision and if it's too stretched, then it's not valid. But then, we're basically just telling the system what to do, and we may be wrong, right? For instance, in the case of sliding, our dynamics might still be valid as long as the rope doesn't catch on something, right? Okay, so how are we going to figure out when our dynamics are valid? Well, what we do is we take another data set, this time in the kinds of environments that we're going to be doing tasks in. But this data set is relatively small compared to what you would need to actually learn all the dynamics well. So once we get this relatively small data set, we can then measure the discrepancy between the predicted states of our dynamics model and the actual states we observe. And if the predicted and observed are close together, then we say, okay, the dynamics model was pretty good. And we give it a label of 1, meaning accurate. And if they diverge, however, then we give it a label of 0 or inaccurate. So then, given this labeled data, we are able to train a classifier. This is a supervised learning problem. And what we do is we take in the state and action that we saw in this data, as well as the local environment. The local environment is represented as a voxel grid where both the rope and the obstacles are voxelized. And then we can learn a prediction of how reliable the dynamics are for that state and action. Okay, so that's really nice. So that tells us what kinds of state and actions we want to avoid when our model's not reliable. But we still might start in a state where the model's unreliable, or we may just be perturbed into that state during execution. So we need a way to be able to escape from these states where we are essentially stuck. Now, why are we stuck? We're stuck because in a state where the model is unreliable, any action you try will be rejected by the classifier. So we can actually sample over possible actions given where we're starting and see if the classifier is going to reject all of them. If the classifier does reject them, we need to recover, otherwise we will never escape this state. And by recover, I mean we need to move to a state where we can actually do some actions. So this is an example of a start state. The unconstrained model has never seen this kind of state before. And as you can see, it rejects all the transitions we try from that state. So how do we actually learn to recover? Well, what we're trying to do is move to a state where the model can actually be trusted. So how do we find such states? Well, we're going to use that same data set that we collected from the environments with constraints to find states where the classifier predicts 0 for many different actions. This does not require getting any more data. It just means that we're going to evaluate actions at states given the classifier we've learned. And then we can see when does a state where essentially we're stuck according to the classifier then turn into a state where we can actually get some non-zero classifier outputs. So if we look for that in the data, then we have examples of when we were stuck and then how we moved to get to a state where we were essentially less stuck or unstuck, if you want to say it that way. And then once we train that recovery network, we can use it to escape from these stuck states. So as you can see here, it's performing recovery. In this case, it's actually lifting the grippers up until the rope is kind of close enough to what we've seen in the training data. And the classifier says, okay, this is good enough. And we run our planner. Okay. So the third part of this framework is the planning and execution. And here I'm just going to go over it at a very high level because it's fairly straightforward. But the idea here is that we're using kinodynamic RRT with the learned dynamics, the unconstrained dynamics. So that's pretty standard there. But we're also including this classifier to reject transitions where the dynamics are unreliable, because again, we don't want to get into those regions. And that produces plans that might look like this, right? So we start out, we lift the rope up, and then we move it over here to the goal. Again, the goal is to move the center of the rope somewhere. Now, during the execution or before we can even start to plan, we may be stuck. So we may need to engage that recovery and replan, and basically recover and replan iteratively until we hit a time limit. So we tried several experiments to show the effectiveness of this method. The first thing we did is test this on what we call rope dragging tasks, where a gripper is holding this red rope, and the goal is to move the end of the rope to some location. So we're holding this side, but the target is for this end here. In dual arm rope manipulation, it's what you saw before in those tabletop scenes. We're trying to move the middle of the rope somewhere. And we compared this method we developed to several baselines. The most important is learning the full dynamics. This is kind of what is traditionally done. You just get all the data and you just try to train a dynamics model that captures everything. And we also compared to ablations of our method. And the metric we're using here is basically the distance to goal after 3 minutes of planning and execution. And we define being within 5 centimeters as a success. Okay, so here's what the results look like. This is for dragging the rope around. You'll see some videos of this in a minute. But this is what the results look like for using the classifier versus not versus full dynamics. As you can see, using the classifier here definitely improves over the no classifier case. And improves vastly over the full dynamics case. This is just reinforcing the idea that trying to learn the full dynamics of the deformable object in a complex environment is a really, really hard problem. And we don't have nearly enough data, at least in this work, to learn that. So we need our method to actually be able to accomplish tasks. And in the dual arm rope manipulation, we also see the benefit of the recovery. So these two lines up here, the purple and the blue, represent results for the classifier using recovery as well. And as we can see, using recovery does much better than the classifier, no classifier. And again, full dynamics is doing the worst here. It's true, however, that a randomized version of the recovery that doesn't use this learnings method is actually performing quite well too. So that suggests that maybe we need more data to actually predict recovery actions better, though we do do a little better than the random version of recovery. So I think the main takeaway from the results is actually with respect to the full dynamics. So what we're basically seeing here is that learning the full dynamics is not tractable for this kind of data set. And what we need to be doing is something more like our method that's able to take advantage of the unconstrained dynamics and still do useful things in constrained environments. Here are a few videos showing this method in action. So I want to first say, I don't want to be misleading here. There's no online perception or replanning happening here on the physical robot. All of this is planned in simulation and then executed on the real world. So before we saw the rope dragging, now you see this hose. It starts out in a state where it's very different from the states we learned the unconstrained dynamics. So we can do recovery, we can lift it up, and then plan to move the center of this hose to the goal here. You can see this is kind of in an automotive setting. It's obviously not as difficult as a true engine bay that's very cluttered, very difficult to move around in. But still we see that our method is able to avoid a lot of this clutter, avoid getting the hose snagged on something, and get to the goal. This would be to position for windshield wiper fluid cable installation, for instance. And we can also do things like moving these straps out of the way. Now the straps are tricky, right? You see how dynamic they are, how they're swaying back and forth. Our model does not account for that, and you see it caught a little bit on the corner there. So this is just showing you a kind of rough idea of what would happen in the real world with these. We still need to do a lot more work to make this robust. Okay, so that was the work on using a learned model of dynamics and then avoiding that model's mistakes. But we don't always want to use a learned model. I think a lot of people think now that that's the only way to go. It's really not. I think that engineers have been using hand-designed models for a long time and will continue to do so for a long time. So this other approach actually addresses something that the first one did not. So if you noticed in the work I just showed you, the state space of the object was known a priori, right? So we were able to say, oh, the rope state is defined by, a set of points on the rope and so on. But if a robot encounters a new object that it hasn't seen before, the state space may be very hard for it to know. So what do we do when we don't actually know how to represent the state space? Well, that's what we're going to talk about with the simple model work right now. So before I get into that, I want to just give a little bit of motivation and just talk a little bit about how engineers and roboticists have been using simple models, right? So something as complex as a car with the transmission and the engine and the friction of the tires, we don't want to deal with all that, right? We don't want to deal with all that complexity. We represent it as kind of a bicycle, kinematic bicycle model often. When we think about humanoids, we definitely don't want to deal with all the complexity of a humanoid when it's doing something like walking or balancing. And so we use simplified models based on inverted pendulum. Same with robot arms. We idealize them as rigid links with perfect joints that can just move kinematically. Again, in idealization, it's a simplified model. And we've proposed our own simple models for deformable objects. So for instance, instead of trying to understand exactly how every wrinkle in a cloth moves when we're manipulating a cloth, we can reduce that cloth down to what we call the geodesic between the grippers, and that model is called a virtual elastic band. And so that's a model we developed for the purpose of doing useful things with cloth that ignores almost the entire cloth and just tries to capture what's important, right? So engineers do this all the time. And what Tom did, Tom is a PhD student in my lab here, is to try to make these simple models work for deformable object manipulation while also accounting for their limitations. And so again, I'm going to give a brief overview of this work. I really encourage you to go to Tom's talk on Tuesday in the session you see here and see the full details and ask him all of the difficult questions. All right, so what we're trying to do in this work is find an action sequence such that the system, which is our deformable object, gets to a goal region. Okay, so standard kind of perform a task, right? But here's the big problem. Well, there's two big problems. First, the dynamics of the underlying system are unknown. Okay, well, maybe we can learn them with some data, maybe not, I don't know. But here's the issue that's even harder. The state space of the underlying system is unknown, right? So we can't even say, here is what this thing is, now learn its dynamics. We don't actually even know exactly what it is. But we have, of course, some information. We can look at it, basically. So we can get some high dimensional observations, basically images called O here of this system. And we have some function that tells us when we're at the goal. Of course, we need to have some function like that, otherwise we can't perform any task. Okay, so you see here on the right an example of a system that with a deformable object. So this is what we call tethered mass. It's a mass, that's the ball, that's on the end of a rope. And the rope is being held by this end here, and it can move back and forth. Okay, so this is a tethered mass. Again, the robot has never seen this before. How are we going to manipulate this tethered mass to maybe bring this mass to some location that we want to bring it to? And our objective is to do this task with as little interaction time as possible on the true system. So it's well known that if I just play with the system long enough and get enough data, I can use some model-free RL method to figure out how to do this test. We all know that. That's been done many, many times. But what those methods are not is data efficient. And when we're talking about robots interacting with things in the real world, we need to be data efficient. So, of course, we have some prior knowledge, and this is where the engineer comes in and says, okay, this thing looks kind of like a model I know about, right? So we're going to say that we have some coarse approximation of the system state, which we're going to call Z, and we have some simple model dynamics. Now, these dynamics could be learned, they could be hard-coded, they could be in a simulator. That's not so important here. What's important is that we have some kind of baseline, approximate, or simple model dynamics. And here for this system, we might pick a cart pole, right? A cart pole can translate in X, and it can swing this pendulum here. That's the theta dimension of the state. All right, so we know everything there is to know about cart poles. We can generate as much data as we want from cart pole dynamics. And in fact, we can actually see, just us, people looking at it, that there is a correspondence between this model and the state of this tethered mass sometimes, right? Sometimes, as up here, this looks nothing like a cart pole, but sometimes it does look like a cart pole. So let's exploit the fact that sometimes it looks like a cart pole to actually control it like a cart pole. Now, the problem is, though, that we don't know where it looks like a cart pole. We're just given this object. We know, hey, something about this looks like a cart pole, but we actually don't know what state and actions can be modeled well with cart pole dynamics. Our future work is to pick which simple system model we use as we're actually performing a task, but we haven't got there yet. We're working on that. Instead, we're just going to say, use this simple model and perform the task. Okay, so this is our framework. There's a lot of boxes. Please don't be overwhelmed. I'm going to go through it in pieces in a second. But the idea here is that we're going to do some offline training and then some online execution and model fitting, or uncertainty prediction, I should say. So offline, we get a data set of observations from the simple model being rendered, and we learn an ensemble of CNNs to estimate the state of the simple system. Now, the reason it's an ensemble is that it gives us a notion of uncertainty about how out of distribution the things we're seeing are. And that is going to be useful here. So when we are online, then we can get observations and use this ensemble of CNNs to predict the state, but also with an uncertainty distribution on it. We can propagate that uncertainty using a UKF, a variant of the Kalman filter here, and then we can consider that uncertainty as a cost in a trajectory optimizer, which is MPPI. But we also need to get the data online as we're executing to fit a GP, which tells us about where in the state space our model is valid and where it's actually going to be erroneous. And the upshot of this is that our model is going to end up being valid in states or that generate observations which look like the training data we've seen. If we see something that looks radically different, like if we train on a rigid link and we see a bent rope, then we're going to say, whoa, I really don't know what's going on. So again, the idea is to stick to what you know and do actions that are going to be valid for the simple model. So here's what this actually looks like. This is the offline training for the tethered mass. Again, it's modeling things as a cart pole. So you see these kind of rigid links, and it's seeing a bunch of different cart poles with different masses on the end, but it's never seeing any bend in the pendulum. Then online, it encounters an observation that looks like this. It fits the simple model to that observation, says, oh, this looks like a cart pole of this length with this mass here. And then it can plan a trajectory and then start to execute it and replan as it's executing. So we tested this work in several experiments, first on the tethered mass, also on this kind of narrow passage rope insertion, and then also a version of that in the real world. And again, the metric that we really care about here is data efficiency. All of these tasks can be learned with enough data using black box RL. We already know that. But what we want to do is really get a big gain on data efficiency. So the baselines were both model-free and model-based. Model-based is Planet, and model-free is curl here. RL methods. We tried with pre-training on the simple model observations. We tried not pre-training on them. Turns out it doesn't make a big difference. And we also tested against ablations. For the tethered mass, we use the cart pole, as I mentioned before. And as you can see, sometimes it looks like a cart pole, sometimes it looks nothing like a cart pole, right? So our goal is to stick to parts of the state space that look like this. And here's what the learning looks like kind of in episodes, right? So as we try the task over and over again, we don't want to hit this target with the rope, I forgot to mention. Anyway, as we try the task over and over again, our method, LVSPC, learns much faster because it's leveraging the knowledge of that simple model than, for instance, these methods here. We see this borne out in the statistics too. LVSPC in blue does better after only 20 trials of the task, just 20 executions of the task. We're already getting above 80% success rate, whereas curl, the closest competitor, takes over 200 episodes to get to the same level. Now it does have highest asymptotic performance. So if you give it enough data, it will basically memorize everything and win. But what we're looking for is success in the low data regime. Another task is to bring the center of the rope into this narrow gap here while avoiding getting caught on these hooks that you see there. The simple model there is a rigid link. And as you can see, LVSPC, after only 20 trials, is able to complete this task. And you'll see the statistics, whereas the other methods are barely getting started on the learning. Again, LVSPC in blue gets about 80% success, close to that. Again, curl takes about an order of magnitude more time, more episodes, I should say. But again, as we know, we'll have highest asymptotic performance. And then we said, okay, well, this is all very nice in simulation, but what about the real world? And so we trained with images that were domain randomized. This is, again, just a simple model, but we are randomizing the background and the colors of everything. And it turns out that does allow us to do things in the real world. So again, we start out, we don't really know what we're doing, and we get caught on the rope. But again, after only 20 episodes, only 20 tries, we're able to perform this task successfully 82% of the time. I think that is a phenomenal success rate with this little training data. Okay, so to summarize, what we've talked about here is learning to avoid a model's mistakes. There's a whole lot of future work to do here, including picking simple models autonomously, generalizing and transferring our learned models between tasks, a whole lot of work to do. But before I end, I really quickly just want to do a quick bonus video and advertise the talk of Yixuan Wang, an undergraduate just graduated from University of Michigan, and also Dale here again. And this talk, this work is being presented on Wednesday. I really encourage you guys to go to the presentation. It's about tracking deformable objects despite severe occlusions. And again, it's using a simple model and some geometric constraints to make sure that our predictions are kind of realistic and plausible. And it really outperforms some very competitive baselines here. And it even does things like consider self-intersection, it considers obstacles, it considers dynamics prediction and making its prediction that can be simple or complex. And it's really great work. And I think a lot of you here who are working on deformable object manipulation will be able to use this in your work. The code is freely available on GitHub, so I really encourage you guys to go to that talk and try this code. Okay, so with that, I'd like to say thank you to my wonderful lab and all of the amazing students that have worked on the things you've seen here, as well as the rest of our work. And I'll open it up for questions.
Yeah, thanks, Dmitry, for the great talks. And we have a question from Rachel, and she's asking, for the first system discussed, what's the boundary of the type of errors that are recoverable versus the ones that cannot be recovered?
That's a really great question. Thank you. Yeah. So it is possible that you get into a state where the rope might be, let's say, under a hook, right? There may be no easy way out, right? You would need a very complex motion planner to, go out under the hook and go around the hook. And our recovery policy doesn't do that. It's just taking kind of a greedy one-step action to say, okay, what's the next best state I can move to from here? So there are definitely cases where it will fail, and you'll basically just keep running recovery over and over and over again, but you'll be stuck in the local minimum. So that's a really interesting problem. It is as hard as the entire problem we're trying to solve, unfortunately. So we don't have a good answer for that at this time.
Okay, thanks. And I actually have a small question. So I think it's great that you presented these two approaches, but I was wondering if you have some hints about when we should go for a learned model and when we should go for a kind of simpler model, as you presented these two possible solutions.
Right. Yeah, it's a very difficult question right now because the boundaries aren't really clear. In the work specifically that I presented, the learned case is most useful when you have a good state representation, right? Because the state representation allows you to understand when your prediction is accurate versus not, right? So if we didn't have that state representation for the rope there, we wouldn't be able to do that method. And the simple model method is really when you're encountering something new and you don't know what it is. So you don't know what the state space is, so you can't possibly do the learned model. So you need to use something else. So that's this specific work, but at a higher level, when should you use simple models or not? I think it really depends on the task that you're doing, right? If the simple model captures a range of behavior that allows you to perform the task efficiently, then that's what you should use. Because first you can understand what it's doing, you can parameterize it and so on. It has all these nice understandable properties. If you can't do that, you're just encountering something that it's just too strange, you don't know how it works, but you can get data, then you should use a learned model.
Okay, thanks. But do you think that the second model, so the simple model, could also generalize to some more complex shapes? Because now you're dealing with the rope, but it seems that it can be also adapted to kind of more difficult shapes if we have some prior, basically. And is it something that you think it's doable with the simple model, and have you tried it?
Yeah, so we haven't tried yet, though we want to move it to cloth. I think that is kind of the next step. And some more complex shapes of cloth or non-homogeneous ropes. I think those are all possibilities. It again becomes a question of, do you have a simple model that's sufficiently useful for doing the task?
Yeah, of course.
And if you don't, then your only choice is to try to parameterize something and learn. And yeah, so I'm definitely interested in that, but we haven't gotten to that point yet.
Okay, great. So I think if there are no other questions, let me check. Yeah, I think we can move to the next speaker. And thanks really a lot for your talk. That was extremely interesting, and we will be watching these talks that you advertised.
Okay, great, wonderful. Thank you for the invitation.
Thanks.